Hello everyone, I am myself Saurav Kumar Jha, and we have started the second unit, that is Fourier transform and Fourier series and Fourier transform. In the last two lecture we have seen Fourier series, what is Fourier series and how we can use Fourier series in expressing any function. So now today we are going to discuss about Fourier transform, and in this lecture we will see how is Fourier transform is derived from Fourier series, or how we can use what is this Fourier transform, how we can use this Fourier transform as a tool in our this subject or in other subject also for expressing our function, or how can use this to convert a function from any one domain to another domain. So basically we will see. See basically when we define Fourier transform, then it's a Fourier transform means see Fourier transform is basically a mathematical model which helps to transform the signal between two different domain. Two different domain what? See, we have two domain. The in Fourier series what domain we are discussing? We are having one domain as f, that means time domain, and one more very common domain which we follow in our electrical engineering or in electronics engineering, that is frequency domain, that is frequency domain. So frequency basically we represent it by what? F, or time period is equal to 2 pi f, or omega is equal to 2 pi by t. This is a various method we can, through which we can express the frequency. So what is, so suppose we have a function, we have a signal, we have a in time domain, and we want to convert that from a time domain to frequency domain. So we should have some tool which will help us in doing this. So that tool is basically Fourier transform. It convert a given function into from time domain to a frequency domain. Next, so here it is written, same thing is written. So there are basic what are the applications of doing this, how we can, what is the use of converting from one domain to another domain. So this is the use basically which is used in engineering physics, such as signal processing, radar and other thing. Okay. Next, see one more thing, also while studying this we know one thing which will come in the further slides. What is the difference between network analysis and network synthesis? See basically when we know the inputs, when we know the input and output, when we know the input and output, and we are required to determine the parameter of the system, then that is basically known as synthesis. For example, see here we know the excitation. What do you know excitation? Excitation is basically input. When we know the input and we know the output, and we want to know how is the network, what is the network, what can be the network, or how it is going to behave, or what system is present within this box, then it is called as network synthesis. But when we are required to find, when we have one excitation, we also have the system or we have the network, and we are required to find the response, then that is called as network analysis. One more thing also, here also you can see network. For example, take one case, suppose while discussing about network synthesis, there is a very common thing you will see, synthesis result can be different. Synthesis result can be different. Why it will be different? See, for example, suppose we were given some excitation and we have got some response, and that from that response excitation we found that the network consists of 4 ohm resistance. After seeing the excitation and response, we determined, or we concluded that this change in behavior can come only because of 4 ohm resistance. Okay. So one can say that okay, the network is going to be 4 ohm, but another someone can also say that it is not a 2 ohm resistance, but instead it is a series combination of 2 ohm resistance. So means someone can get 4 ohm, or someone else is getting 2 plus 2 in series. So same, see, although the result is same, both in both the cases the final series will final resistance will be 4 ohm also, but in synthesis this is also correct, this is also correct. So that mean, or someone can get 2 8 ohm resistance in parallel. So there can be different method, or there can be different combination of this resistance to get 4 ohm. Therefore we can say synthesis may be different. Suppose there is not a fixed for a single excitation and single response we can have different synthesis or we can have different network. So, just keep this thing in mind. Next. Okay. So, in Fourier series what we have seen that we can represent any periodic signal in a combination of sine and cosine, different combination of sine and cosine with different frequencies. Okay. So, this is basically what our Fourier series. So, now we will see how we can convert that Fourier series into Fourier transform in the later lectures. So, this was the coefficient we were getting, two coefficient AK and BK I have seen. We were having three things, A naught, AK and BK. So, AK and BK already represented here. A naught was basically what? B naught was basically the average, or you can say the DC value of a given signal or DC value of a given signal. Okay. Next, see, also we have converted this form into, this was the common form, change this is Cn. We have converted this form into what? Another form. How we have got this form? See, we have converted this form into this form. How you will get this? How you will get, see basically you have to remember one thing, cos A plus B is equal to cos A into cos B minus sin A into sin B. So, using this relation we have converted the common trigonometrical form into a cosine form, okay, where Cn represent an square plus bn square and phi n square represent angle tan inverse bn by n. See how we can do it. See, suppose we are having already having one cosine term, here we are having sine term. Okay. So, now if we divide the whole combination by an square plus bn square, if we divide this whole combination by this term, then what will become, if this is cosine, this will become sine, and if this is sine, this will become cosine. So, we will get cos A into cos B plus sin A into sin B. So, we will get this combination. Once we get this combination, we will replace this by this conversion. Okay. Also very helpful tool which we will be using further while while using Fourier transform. This is Euler's formula. What does it say? See, Eix basically is represented by cos x plus I sin x. This representation you have to remember, how we can, through Euler formula, how we can represent Eix into cos and sin. So, this is the representation here, where see Eix, when you write like this is what is this is one real plus imaginary term ji. So, this is represented in two ways, either you can write in amplitude or angle form, or you can write as A plus B form. So, this is basically representation. Now, one more tool which will be very helpful is basically Euler's formula was Taylor series. See, what is Taylor series? See, Taylor series basically a representation of it exponential to the linear x. Okay. Similarly, one more tool is even function, odd function. This is how we represent. So, these are basically Taylor series expansion. You have, if you remember, we were having Taylor series expansion. So, this is how we represent Taylor series of three terms cos of Ex. Why we are writing this? Because just now we saw that we can represent Eix into cos x plus sin x. Okay. So, what we will do? We will write the Taylor series of cos x and sin x both in in even and odd parts. So, what we have done here? See, so this is Taylor series of cos, this is Taylor series of sin, and finally combining we have derived this. So, if someone asks you from where this derivation come, if we are required to derive this, that Eix is equal to Euler's formula, then we can say we have derived this from this method. Using this method we have derived. We have first written the exponential of Ex, Taylor series expansion of Ex, then we have got for cos x, sin x, and we have replaced this term and we have got this final cos x plus I sin x. Okay. Okay. So, now why we have to go to Fourier transform? Why, what was the disadvantage of Fourier series, or what was the limitation of Fourier series because of which we were required to shift towards Fourier transform? That is basically in Fourier series, if you remember, what was the condition? That the condition was Fourier series can only be written for a periodic signal. if the signal is non-periodic, we cannot represent at signal in the Fourier series form. So, in order to so it was one of the limitation of Fourier series. So, what we have done, so this is what is written here. So, what we are required to, we have to make some modification so that we can use even these tools. Fourier series was also a tool, but this tool came with an limitation. So, what we are required to do is we should make some modification in this so that we can go for some non-periodic signal as well. So, Fourier transform is a method in which is applicable for non-periodic signal as well. Okay. So, let us see, this is the same thing just we have written. See, so basically, so when we are going for Fourier transform, so we are not making use of the what see, basically there was two form of Fourier series, two form, one was exponential form and another was trigonometrical form. So, basically, so this is complex form you can say, or you can say is a exponential form. So, we are modifying this complex form so that we can get this Fourier transform. So, see, okay, before getting that Fourier transform, as we were having some condition for existence of Fourier series, similarly in Fourier transform also we have some condition that is basically called as what Dirichlet condition. In Fourier series also it was Dirichlet condition, in Fourier transform also we are having similar conditions for which for existence of Fourier transform. So, see, what is the change in Fourier series, what is the condition, first condition, it was Fourier transform does not exist for all non-periodic signal, hence for a function x to be Fourier transform, the following condition called should be satisfied. Okay. So, suppose it is for all non-periodic signals, okay, does not exist for, so what are the different conditions which are required to get the Fourier transform of a signal. So, see, the function x t is absolutely integrable over the time interval. See, this is the first condition, it should be what absolutely integrable. See, one more thing, what do you mean by absolutely integrable? So, when I say, see, that means if a function gives finite value, if a function gives finite value for integrating this, then we can say this is example of what? Example of a absolutely integral survey. So, see here, so also if you remember from the unit 1, basically we had three types of signal, one was energy signal, second was power signal and third was neither energy nor power signal. Okay. So, if you remember energy, if you remember, then energy signal, what was energy signal? See, what was the power signal, what was the non. So any signal which is having finite magnitude, which is having finite duration signal, or any signal which is having decreasing amplitude. So, all those type of signal, basically if it was, I have told you a shortcut through which we can determine which one is the energy signal, which one is the power signal, which one is the neither energy nor power signal. So, for energy signal, what I have told you? I have told you, see, if any signal that is finite duration, that is having finite duration, or if it is having decreasing magnitude, then both of the signal will come under the category of energy signal. Okay. Then what was the neither energy nor power signal? So, neither energy nor power signal is one signal which is having at any duration of time, if at any duration of time, if the magnitude of a signal is infinite, then that signal fall under the category of neither energy nor. For example, 10t, you know, graph of 10t, 10, 90 is what? Infinite, or 1 upon x, this will also for x equal to 0 it will go infinite. So, these type of signal which is having amplitude or magnitude infinite for any time duration or for any particular instant of time, then that is called as what? Neither energy nor power signal, and excluding this all the signal which will fall in the category of power signal. So, example of power signal, what is example of power signal? So, example of power signal is one ut, if you remember ut is what? Unit step signal is example of what? Power signal, because see, because it is not energy signal, because it is not, neither it is having decreasing amplitude because amplitude is constant, neither it is having what? Fixed duration, because it is going from 0 to infinity. So, it does not have any of these properties. So, it is not an energy signal. Check for neither energy nor power signal. What was the neither energy nor power condition? It should have infinite magnitude at any instant of time. See, this is not having infinite value at any instant of time. So, this comes under category of power signal. So, that means also if you remember, you cannot integrate what is the, if you try to integrate this energy signal, if you try to integrate this power signal, so you will not be able to find the, it is not absolutely integrable. Power signal are not absolutely integrable, because we can see we cannot integrate this unit step signal. So, what does it means? So does it mean that we will not be able to find, the Fourier transforms of power signal? No. See, as per the condition, it is saying that the function is absolutely integrable over the time instant for that. So, this is one fourth point is very important. See, the Dirichlet condition are the sufficient condition, but not necessary condition. It is the sufficient condition. That means you cannot say that if a signal is not integrable, then that it means we are not able to find the Fourier transform. We will be able to find Fourier transform. The only change will be we will require to, we cannot directly find it, we will require to have some properties. We have some properties of Fourier transform. So, using those properties we can easily find the value of Fourier transform. Directly it is very difficult to find. So, always remember, in case of Fourier transform, all the condition, these three condition are sufficient condition, but not necessary condition. So, just remember this point. Rest 2 points are same. What is the second point? The function has finite number of maxima minima, and the third point is function has finite number of discontinuities. So, these both condition are similar to that of Fourier series. It should have finite maxima minima and it should have finite number of discontinuities. But the only change from Fourier series to Fourier transform is that here the condition is sufficient, not necessary. Okay. So, thus you have to keep this thing in mind. Now, next. So, see the same thing what I was telling. See, this is the second condition, sorry, this is the first condition. So, this is a necessary condition, sorry, sufficient condition, not necessary. This is the sufficient, this is the first condition, it is only sufficient condition, not necessary condition. So, always just keep this thing in mind. So, now, so how we can move from Fourier series to Fourier transform, or how we can, what is the basic idea for going for Fourier transform using the Fourier series. So, see, basically when we say, suppose this is a signal, it is from minus T naught by 2. So, T naught by 2, this is a time duration, this is a basically a time duration, this is a what, a signal. As you can see, the signal is not periodic, but if we want, suppose if this signal was periodic, what does it mean? This is Ft, this is Ftt. So, suppose if this signal was periodic, so we will be able to write the Fourier series for this. Okay. So, in order to use suppose, okay, now suppose what is the time period for this signal? Suppose here also time period is T naught, here also time period is T naught, here also time period is T naught. Okay. So, suppose if we try to make this time period infinite, if we say this, if we make the time period what, infinite. So, what does it mean? Infinite time period means what, that this signal will be repeated after how much duration of time? It will after infinite times. So, we can say basically a periodic signal or a non-periodic signal, is one in which it can be repeated, which will be repeated after infinite duration of time. Okay. So, using this assumption, we will convert this into the Fourier transform. See how? See, for this, suppose if you want to write for this, if you want to write Fourier series in exponential form, how will write Cn is equal to 1 upon T naught okay. This is how we will write, this is how we will write ft, sorry, this is ft will write like this, okay, sorry, this is for this, so this will be, we are notifying it by f tau. So this is how we will write Cn, this is how we will write Cn. Now suppose again here if we write like this, so from this if we now let us shift it to so this is what we will get as ft. Now suppose if I write it like this as is equal to 1 T naught minus infinite to infinite f t dt. What we write? It f t here it over j n omega naught. See, if this signal, if you integrate, if this, see basically if you integrate this signal which is from minus infinite to infinite, or if you integrate this signal for t naught duration, in both the cases you will give same output, because see because this signal is existing from minus t naught by 2 to t naught by 2. So if you integrate this from minus t naught by 2 to t naught by 2, or if you integrate this from minus infinity to infinity, you will get the same output, okay. Again suppose now either this is, if you try to increase the frequency, so what will happen? Let make f t is equal to 2 f t, okay. So what will happen? The signal will be little closer. Again if you frequency will get reduced if you increase the time period, or if you decrease the time period, frequency will, see what is the relation between f is omega is equal to 2 pi by t, omega is 2 pi by t. So if you increase the time period, omega will, frequency will reduce, okay. So similarly if we keep t is equal to infinite, so we can say this can be written as it 1 minus j omega t n omega naught. So this is basically we convert it and we write it as, so here these both thing can be same only in one case, that what is f dash t, function of f dash t is make is f infinity, then we can get f tau t, frequency same as f t, and the both combined can be written as integration minus infinity to infinity f t e to power minus j omega t dt. This is basically what we call as Fourier transform means. This is what basically Fourier transform means, okay. And this is basically what Fourier transform means. This function f t is equal to e to power minus j omega t dt, okay. Now next, see same thing is been derived here. We have kept the value and see. So what happened in Fourier series? What we are having? If you write it like this, it was discrete spectrum, and in Fourier integral, if you replace this time period by infinite frequency, or you have increased the time period, then the frequency will be what? Very much less. It will be very much closer. So see what happened basically. See, suppose some signal is like this. This is the spectrum. Now suppose if you increase the frequency to 5 times, if this is f and this is 5f, then how will 5f look like? It will look like this. It will look much closer. Again if you increase the frequency 10f, so it will be like this. So, it will become what? It will again, if you increase the frequency, then it will look like what? A continuous spectrum. If you increase the frequency, it will look like a continuous. So, same thing here also. So, this form is basically, so this is what we have derived now. This is Fourier transform, that is called analysis. When we have the input and we have the system, we have the network, we know the function, we know the input, we know the function, we know the input, then we can find out fj omega, that is called analysis. And when we know the output, we know the input, we know the output, and we are required to find the network, or that is called as synthesis. We call as synthesis. Okay. Next. So, this is again continuous spectrum, and this example basically what? Take one example. Suppose if you want to find Fourier transform of this function, this is what? A unit impulse or pulse which is from -1 to 1, then how you will find out? See, keep here function f t. So, it exists between what? -1 to 1. So, we keep here e to the minus j omega t dt, it will come like this. So, basically this is the conversion of what? A pulse is basically represented in Fourier transform as 2 sin omega by omega. Take one more example. This is basically e to the power minus alpha t. If you want to integrate similarly, see here what will happen? E to the power minus alpha t, and here we have e to the power minus j omega t. So, it will, as you know, power is basically added. So, it will become e to the power minus alpha plus j omega t, and here it will get it as alpha plus j omega. So, remember the integration, is very much useful, that integration of e to the power minus alpha t means Fourier transform of e to the power minus alpha t is 1 upon alpha plus j omega. So, this is very useful, many places you will be required to find this. Okay. So, in next lecture we will see some properties, what is the different properties of Fourier transform, and using that property how easily we can find out Fourier transform without doing this integration. See, at every place you have to do, you are required to do integration. So, if you know the properties, so we can directly seeing the properties, we can say what is the Fourier transform, or what is the nature of the Fourier transform. So, in next lecture we will see what are the different properties of Fourier transform, and using the property how we can get the result easily. Thank you.